Welcome to the Deep Dive, the show where we take a complex topic, grab a stack of the best sources, and really distill it all down into the fascinating nuggets you need to be truly well-informed.
That's the plan.
Today, we're embarking on an incredible journey. It starts with a seemingly simple plant, but, it quickly unravels into this world of precise chemistry and, frankly, ingenious engineering.
It really does.
We're talking about how you get from a fresh cannabis plant, which surprisingly doesn't directly contain the active compounds many people are looking for, all the way to the sophisticated oils, edibles, and concentrates that are, well, everywhere today.
Yeah, it's a real transformation. It's a process of unlocking the plant's hidden potential, really moving it from its raw natural state to a highly refined and specific product.
Exactly.
And our mission today is to make sense of these intricate chemical transformations and the surprisingly diverse array of methods used to achieve them. We'll look at everything from, traditional home techniques you might be familiar with, right up to the most cutting-edge industrial processes, all with the goal of extracting key nuggets of knowledge for you, our listener, so you can understand the science behind what's actually in these products.
That's our goal. And for this deep dive, we're pulling our insights primarily from two really solid scientific studies.
Yeah.
One's called Cannabinoid Decarboxylation, a Comparative Kinetic Study.
Yeah.
And the other is a comprehensive comparison of industrial cannabinoid extraction techniques.
Right, good sources. They really lay out the science behind transforming that raw plant material into usable products.
And we're excited to unpack that journey for you. So let's kick things off with this fundamental chemical transformation, the thing that unlocks the potential of these cannabinoids. It all starts with understanding what's actually inside a fresh cannabis plant.
Yeah.
Because when we think of a fresh plant, we might picture it's just brimming with THC or CBD, ready to go.
Yeah.
But that's not quite the full story, is it?
No, that's a really crucial distinction. What's naturally occurring in the fresh plant are primarily the acidic forms of these compounds. We're talking about delta-9 tetrahydrocannabinol acid, or THCA, cannabidiol acid, CBDA, and cannabigerol acid, CBGA. You can think of these as the precursors.
Starting point.
Exactly. They are biosynthesized, basically built by the plant, and they accumulate mainly in those tiny crystal-like glandular trichomes. You see them on the surface of the female plant's buds, particularly in the flowers.
Right. Sticky bits.
Those are the ones.
Yeah.
These acidic forms are naturally built up in the plant from an initial master precursor, CBGA, through a very precise internal biological pathway. You really only find minimal amounts of these compounds in other parts, like the leaves, roots, or stems. The action is in the trichomes.
So, okay, if these are the precursors, the locked versions, why do we need to transform them? Why aren't these acidic forms, the THCA and CBDA, what people are typically interested in, especially from, say, a therapeutic perspective?
That's the real aha moment for a lot of people. Now, while some specific pharmacological properties have been attributed to the acidic forms themselves, there's research on CBDA and THCA specifically. It's generally their neutral counterparts. So, delta-9 tetrahydrocannabinol, THC, cannabidiol, CBD, and cannabigerol, CBG, that are considered to be of wider therapeutic interest.
And why is that?
The main reason is biological access, basically. These neutral forms can more easily cross the blood-brain barrier. That's essential for many of their desired effects on the body and mind.
Gotcha. So they can get where they need to go.
Precisely. And because of that, this transformation step has become absolutely crucial in the cannabis industry for creating effective products.
Okay, so this vital transformation, this decarboxylation process,
Right.
how does it actually happen? Can you simplify the chemistry for us a bit?
Absolutely. Decarboxylation is, at its core, a chemical reaction. It literally removes a carboxyl group. You can picture it as a small chemical tail, a COH group from the acidic cannabinoids.
Takes off a tail.
Okay. Right. When this tail is removed, usually by heat, it releases carbon dioxide, CO2, and that converts the acidic form into its neutral active counterpart. I sometimes think of it like taking off a coat to reveal what's underneath.
I like that analogy.
The plant makes the cannabinoid with its coat on, the acid group, and we need to take that coat off to get the active form we're usually after.
And before we dive into all the industrial complexity we'll get into later, how did, say, recreational users historically achieve this? I mean, they weren't using fancy lab equipment, right?
No, definitely not. Traditionally, it's been achieved through pretty simple methods, smoking or vaping, for instance. The heat from the combustion or the vaporization instantly triggers that decarboxylation process.
Where the heat does the job.
Exactly. And even baking cannabis into edibles involves this process. The heat from the oven over time triggers the conversion from the acidic form, THCA or CBDA, into the neutral active compounds, THC or CBD.
So cooking it basically activates it.
Pretty much. These traditional methods provide a relatable starting point before we dive into the much more precise and complex industrial approaches that are all about achieving consistent, high-quality results every single time.
Okay. Now, beyond this before and after of the main cannabinoids, the sources also talk about stability and byproducts, which sounds really important for product quality. Can you tell us about cannabinol, or CBN? What's its story?
Certainly. Cannabinol CBN, it's actually a relatively minor constituent in the fresh plant material. It's primarily an oxidation product of THC, meaning it forms when THC degrades, breaks down, particularly when the cannabis is stored for a long time or exposed to air and light.
Ah, so it's like a sign of aging.
That's a good way to put it. What's important to understand is that CBN content tends to increase as THC degrades. So its presence often serves as a kind of chemical marker. If you find a lot of CBN in cannabis that's supposed to be high in THC, it often indicates that it's been poorly stored or stored for too long.
So it signals that the THC is broken down. Not ideal if you're looking for THC.
Exactly. If you see high CBN in a product meant to be high in THC, it's a pretty clear sign the product might not be as fresh or as potent as you'd hope. It's definitely an indicator of quality degradation.
Good to know. And what about other minor cannabinoids we sometimes hear about? Things like CBC or delta-8 THC. Are they part of this main decarboxylation story?
Well, our sources mention these other minor components, cannabichromine, CBC, delta-8 tetrahydrocannabinol, 8-THC, delta-9 tetrahydrocannabinovarin, 8,9-THCV, or cannabidivarin, CBDV.
Right.
But interestingly, none of these specific phytocannabinoids naturally occur in the cannabis plant at really significant concentrations, either in their initial acidic form or as their neutral counterparts after simple heating.
So they're just not there in large amounts to begin with?
Generally, no. While they might be present in trace amounts or sometimes chemically converted in a lab setting, delta-8 is a good example of that. Recently, they aren't the primary compounds we're focusing on when we talk about natural abundance or the direct impact of standard decarboxylation for activation. The main story, the big transformation, is really about THCA, CBDA, and CBGA turning into THC, CBD, and CBG.
Okay, that clarifies things. So we've established what decarboxylation is and why it's so vital for unlocking the plant's potential. Now, let's take that deep dive into how industries actually control this chemistry for optimal results. Because this isn't just about getting the active compounds out right. It sounds like it's a really crucial step that directly impacts the final product's potency, purity, and, well, its value.
That's absolutely right. Decarboxylation isn't just, something consumers do anymore. It's an absolutely crucial, foundational step in the commercial cannabis industry. The precise control over this process directly impacts not only the extraction yield, like how much usable material you actually get out, but also ensures the full conversion of those cannabinoid acids into their desired neutral forms for all sorts of new products. And these products are increasingly aimed at therapeutic use, which, helps move the conversation away from some of the stigmas traditionally associated with recreational use.
Right, more towards medicinal or wellness applications. And when do they actually perform this decarboxylation in the industrial process? Is it before they extract the compounds from the plant or after? Does it matter?
It can actually be done at either stage. The decarboxylation process can be performed on the plant material prior to extraction, so you heat the raw plant first, or it can be done directly on the extracted oleoresin, which is basically the crude oil you get after an initial extraction step.
Okay, options. Is one preferred?
Generally, yes. Performing it on the plant material before extraction is often preferred, especially when it's going to be followed by supercritical CO2 extraction, or CCO2 as it's often called.
Ah, okay. Why is that the preferred method, especially with that CCO2 extraction? What are the practical advantages for a producer doing it that way?
There are two really key advantages that make a big difference for efficiency and the quality of the final product. First, doing the decarboxylation on the plant material before extraction allows for the removal of moisture that's naturally present in the plant.
Drying it out first.
Exactly. Drying the plant is beneficial for almost any extraction method. It just improves efficiency overall. But second, and this is crucial for CCO2 extraction, the cannabinoid acids THCA, CBDA are actually more polar than their neutral counterparts, THC and CBD.
Polar, meaning like water-soluble.
Sort of. Think of it like having different stickiness properties. Nonpolar solvents like supercritical CO2 are really good at dissolving other nonpolar things. Since the neutral cannabinoids THC, CBD, CBG are less polar, they become much more soluble, much easier to dissolve in that nonpolar CCO2.
I see. So you decarb first, make them less polar?
And then the CCO2 can grab them much more easily. So by decarboxylating first, you're essentially making your target compounds far easier to dissolve and extract using CCO2. This significantly improves the overall extraction efficiency and the yield. For a producer, that translates directly into cost savings and higher output. It just works better.
Okay, that makes perfect sense. Now, here's where it gets really interesting, I think.
Yeah.
The experimental insights into the key factors that influence this decarboxylation. It sounds like temperature and time are absolutely critical players, but just how dramatic is their impact?
Oh, they are critical, and the relationship is quite dramatic. Decarboxylation, while it can happen slowly at lower temperatures, say at 80 degrees Celsius, which is about 176 Fahrenheit, it significantly accelerates as you increase the heat. For example, the studies we looked at showed that THCA was completely decarboxylated, fully converted, in 90 minutes when it was heated at 120 degrees Celsius. That's 248 F.
Okay, hour and a half.
But if you crank that temperature up to 160 degrees Celsius, which is 320 F, the exact same conversion is achieved in just 20 minutes.
Wow. 90 minutes down to 20. That's a huge speed up.
It is. It clearly demonstrates the powerful impact of temperature on the reaction speed. You can achieve the same result in, less than a quarter of the time just by using higher heat.
That acceleration with heat is incredible. It almost makes you wonder, well, why doesn't every producer just blast their material at 160 degrees C or even higher and get it done super quick? What's the catch? Is there a hidden challenge or a downside if you simply crank up the heat?
That's precisely the dilemma, and it's a big one. While the conversion definitely speeds up, we also observe a critical phenomenon often described as a peak and drop.
Peak and drop.
Yeah. So for instance, the concentration of your desired compounds, like THC, will reach a maximum level as the conversion happens. But then, particularly at temperatures above 100 degrees C, 212 F, its concentration actually starts to drop again.
It goes down after peaking.
Yes. This is absolutely vital information for producers because it means there's an optimal window. If you go too slow, you lose efficiency, it takes too long. But if you go too fast or too hot for too long, you actually start losing your valuable product. It starts to degrade or disappear.
Why does it drop? Is it just converting into something else less desirable, or is it actually being, lost altogether?
It's primarily being lost, which is obviously a major concern for anyone trying to make a high-quality product. There's a significant loss of total cannabinoid content observed at these high temperatures.
How's it being lost?
Well, the primary reason seems to be the evaporation of the neutral forms themselves. Think about it. THC has a boiling point around 157 degrees C, 315 F, and CBD's boiling point is a bit higher, somewhere between 160 and 180 degrees C, 320, 356 F.
Right, near those high processing temperatures.
Exactly. When you're operating at or even slightly above these temperatures during decarboxylation, the desired compounds, the THC and CBD you just created, can literally start boiling away. They turn into vapor and escape the material.
Wow, just evaporating away.
Pretty much. And in addition to evaporation, there's also evidence that other unidentified byproducts are forming. These are essentially degradation products, things you definitely don't want in your final extract. So it's a combination of evaporation and breaking down into other stuff.
Okay, that's a lot of potential loss. Can you give us a concrete example from the studies, something to really illustrate the stakes here for a producer? Losing products sounds bad.
Yes, the numbers are quite stark. The studies measured the sum of molar concentrations of THC plus its precursor THCA plus its breakdown product, CBN, basically, the total amount of related cannabinoids you'd expect.
Okay.
And they found it could decrease significantly. For example, that total amount could drop by as much as 78% after just 60 minutes of heating at 160 degrees C.
78%, that's huge.
It is. Imagine a producer has spent, thousands of dollars on a batch of high-quality plant material aiming for a really potent oil. If they accidentally overheat it by just a few minutes or hold it at that high temp for too long, they could potentially lose 3/4 of their main active ingredient.
That's disastrous.
It's not just a minor inefficiency, it's a catastrophic financial hit for them. And it results in a product that simply won't deliver the promised effects or potency to the consumer. And for CBD and CBG, the study showed potential losses could be even more severe under similar conditions, sometimes over 90%.
Over 90% loss?
Yeah. It truly highlights the razor-thin margin for error here. It's this delicate balance that producers need to achieve. You absolutely want to fully convert the acidic forms to get the activity, but you have to do it without degrading or evaporating away the neutral ones you just made.
So finding that sweet spot of time and temperature, it really sounds like an art form, doesn't it? But backed by some very precise science. It reminds me a bit of baking the perfect cake. Too little time, and it's raw inside. Too much time or too hot, and it's burnt.
That's a great analogy.
But here, burnt means literally evaporating away your most valuable compounds into thin air. I can only imagine the pressure on these industrial chemists and engineers to hit that tiny window of perfection, batch after batch after batch.
Exactly. Careful control of both time and temperature is absolutely essential to maximize the desired cannabinoid content while minimizing that degradation and loss. The studies actually pinpoint optimal times for reaching maximum CBD and THC concentrations at different temperatures, illustrating this delicate dance.
Can you give an example?
Sure. For instance, you could achieve the maximum concentration of CBD if you heated the material at 80 degrees C, but it would take a very long time, 24.7 hours, according to the study.
Over a day.
Right. But if you increase the temperature to 160 degrees C, that maximum CBD concentration is reached in only 9 minutes.
9 minutes versus 24 hours? Huge difference.
Huge. And it's similar for THC. The maximum concentration was observed at 80 degrees C after about 2 hours, but if you go up to 160 degrees, you hit that peak in just 6.5 minutes.
So much faster, but you have to stop it right on time.
Precisely. It's all about balancing the speed of conversion with preserving the integrity of the compounds and, crucially, not letting them literally vanish into thin air through evaporation or degradation. It's a high-stakes optimization problem.
Okay, so temperature and time are huge. What about the sheer amount of material being processed? Does the bed depth, essentially how thick the layer of plant material is in the reactor or oven, make a difference? Does packing more and change things?
It absolutely does, and it's one of those deceptively simple factors that can have a really big impact on the efficiency of the process. The studies clearly showed that using a larger amount of material, for example, if you quadruple the amount, leading to a 4-fold increase in the depth or thickness of the bed, it significantly slows down the decarboxylation process. For instance, at 140 degrees C, 284 F, the conversion of THCA, CBDA, and CBGA after 60 minutes was only around 88–89% complete in a deep bed. But in a much shallower bed under the same conditions, the conversion was practically complete.
So thicker layer, slower reaction. Why is that? Does it just come down to basic physics like heat getting through?
Precisely. It's largely attributed to slower heat transfer rates through that deeper bed of plant material. Imagine trying to evenly heat a huge, thick pile of something versus a thin layer spread out on a tray.
Right, the heat takes longer to get to the middle.
Exactly. Heat simply takes longer to penetrate uniformly through a deeper bed of insulating plant material. On top of that, with a deeper bed, there's also a reduced surface area exposed to any air circulation within the oven or reactor, and less surface area for evaporation to occur from. Both of these factors impact the chemical reaction rates, the kinetics, and also affect the rate at which certain byproducts or evaporated cannabinoids might escape. So this simple physical factor, how thick the layer is, means a larger batch can take much longer to process correctly, or it might yield less if the time isn't adjusted properly.
That makes perfect sense. It's not just chemistry, it's heat transfer too. Now, what about the atmosphere? Does the presence of oxygen during the reaction play a role? Does it help or hurt the process?
It definitely plays a role, and it's a very negative one. The presence of oxygen during the reaction significantly impacts the kinetics, basically slowing the desired reaction down.
Better with oxygen.
Yes. The decarboxylation rates for THCA, CBDA, and CBGA were found to be significantly higher when oxygen was absent compared to samples that were heated in open beakers exposed to air.
How much higher?
Quite a bit. For THCA, the rate was 122% higher without oxygen. For CBDA, it was 102% higher, and for CBGA, 98% higher. Oxygen essentially interferes with the process and seems to promote side reactions or degradation pathways.
Wow, double the speed, roughly, without oxygen. So, practically speaking, What does that mean for industrial producers? Does this push them towards using special equipment? Are there significant challenges or costs associated with creating and maintaining those oxygen-free environments?
It strongly suggests why many industrial operations invest in using vacuum ovens or systems flushed with an inert gas like nitrogen. These controlled atmospheres help protect the cannabinoids from oxidation, which, as we mentioned, can both degrade the desired compounds like THC into CBN and also slow down the main decarboxylation reaction itself.
So it's worth the effort.
For many, yes. While implementing vacuum systems or inert gas flushing definitely adds to the equipment cost and the operational complexity, the payoff is often a significantly more efficient process, a higher quality final product with better yields, and less degradation. It's really an investment in product integrity and ultimately their bottom line.
This all sounds incredibly precise. Getting data like 122% faster requires some serious measurement.
Yeah.
How do scientists actually study this in the lab to get such accurate data points on reaction rates and optimal conditions?
Yeah, it requires really advanced analytical lab techniques and rigorous experimental design. Typically, they start by carefully preparing the hemp or cannabis material, often milling it down to a consistent fine particle size. This ensures uniformity.
Okay.
Then precisely weighed samples of this milled material are placed into small containers like vials or crucibles. These are then heated in specialized laboratory ovens that maintain very accurate and stable temperatures for set periods of time.
And for the oxygen-free tests?
For experiments testing the effect of oxygen, the samples are often sealed, maybe in special foil bags or sealed vials, and then flushed thoroughly with nitrogen gas to remove all the oxygen before they're sealed and heated. After the specific heating time is up, whether it's minutes or hours, the samples are immediately cooled down rapidly, often in an ice bath or freezer, to instantly stop the chemical reaction.
Quenching the reaction.
Exactly. Freezing the reaction at that specific time point is crucial for accurate data.
And then how do they know exactly how much of each cannabinoid, the THCA, the THC, the CBN, is actually present in that sample? Down to such precise percentages, it seems almost like, well, chemical detective work.
It truly is. That's where highly sensitive analytical machines come into play. They use techniques like high-performance liquid chromatography, often coupled with mass spectrometry. You'll see it abbreviated as HPLC or LCMS.
Okay, fancy machines.
Very. These instruments can first separate all the different compounds present in the extract taken from the heated sample. Then, the mass spectrometer acts like a highly specific scale, identifying and measuring the exact amount of each specific cannabinoid based on its unique chemical fingerprint, its mass.
So it can tell THCA from THC from CBN. Precisely.
Absolutely, and quantify each one. By comparing the signals they measure to certified reference standards, pure samples of known cannabinoids at known concentrations, they can generate incredibly accurate data on how much of each compound is present at any given time point during the heating process. This meticulous quantitative approach is what allows them to map out the reaction kinetics, pinpoint those optimal time and temperature conditions, and understand the intricate chemical transformations we've been discussing. It's this rigorous science that provides the foundation for optimizing the process on a commercial scale.
Fantastic. So once we've navigated that crucial decarboxylation step, maybe heating the plant material just right, the next big challenge is actually getting the good stuff out of the plant material. This brings us squarely into the world of cannabinoid extraction techniques. Now, before we dive into the specific methods, just remind us again, where exactly are these valuable cannabinoids primarily found in the plant?
Right. It's important to remember they aren't evenly distributed. Cannabinoids are primarily synthesized and then stored or accumulated in those glandular trichomes we mentioned earlier.
The tiny mushroom-shaped glands.
Exactly. Those crystal-like glands found mostly on the surface of the female plant's buds, especially concentrated in the flowers. When you handle the buds, these trichomes can rupture and release that sticky, cannabinoid-rich resin.
Okay.
You'll only find really minimal amounts of this resin, and therefore the cannabinoids in the other non-glandular tissues, like the leaves, the roots, or the stems. So any efficient extraction method really needs to focus on effectively accessing and removing the contents of these surface trichomes.
Knowing that they're mostly on the surface in these trichomes, what are the key things a producer has to consider when choosing any extraction method? I imagine it's definitely not a one-size-fits-all situation. There must be trade-offs.
Absolutely not one size fits all. Choosing the right extraction method is critical, and it involves balancing multiple factors that directly impact their bottom line and the quality and type of the final product they want to create.
Like what?
Well, producers have to consider the overall extraction yield. That's basically how much total mass, oil, or resin they get out relative to the starting amount of plant material. But perhaps even more important is the extraction efficiency,
Efficiency meaning?
meaning the proportion of the target cannabinoids, like CBD or THC, that they actually manage to extract compared to the total amount that was present in the plant to begin with. You want to get as much of the good stuff out as possible.
Right, leave less behind.
Exactly. Then there's the quality of the extract itself. This includes its purity, but also the presence or absence of other desirable compounds, like the terpenes and flavonoids that contribute to aroma, flavor, and potentially the entourage effect. Or conversely, the presence of undesirable compounds like chlorophyll or waxes that might need removing.
Makes sense. What else?
Environmental impact is increasingly important. How much waste is generated, the energy consumption. Safety for the workers operating the equipment is a huge factor, especially with flammable solvents. And of course, scalability. Can the method be efficiently scaled up to handle large production volumes? Ultimately, the desired final product really dictates the method. Are they aiming for a pure CBD isolate, a full spectrum oil, a specific cannabinoid profile for a tincture, or maybe a concentrate like shatter or wax? Each goal might point towards a different optimal extraction technique.
Okay, a lot to juggle. Now, before they even start the main extraction, is there any preparation involved for the plant material itself? Does simply grinding it properly make a difference?
Yes, pre-treatment of the plant material is often a very important step to maximize the efficiency of the subsequent extraction. Simple physical pre-treatment can involve just basic air drying to reduce moisture content, and then powdering or milling the plant material.
Why powder it?
Powdering increases the overall surface area of the material and makes those trichomes more accessible for the solvents to penetrate. By making it into a powder, it even allows for some minimal extraction from bits of non-glandular material that might contain trace amounts, stuff that wouldn't normally be targeted effectively in whole buds.
So, more surface area, better contact. Is there anything more advanced than just drying and grinding?
Yes, a more advanced physical pretreatment method is freeze drying, also known as lyophilization. This process removes water as ice vapor under vacuum, and it produces a powder that often has a relatively uniform particle size and higher surface area compared to air drying and grinding.
And that helps how?
This higher, more uniform surface area specifically improves the access of certain solvents, like supercritical carbon dioxide, during the extraction phase. It allows the CO2 to penetrate the material more effectively, thereby increasing the proportion of cannabinoids extracted. Basically, you get more out, leaving less valuable material behind. It means less waste and better efficiency.
That makes sense for physical prep drying, grinding,
Yeah.
maybe freeze drying. But you mentioned something even more advanced earlier, something called pulsed electric fields, or PEF.
Right.
How on earth does that work, and why would someone use it? It sounds quite futuristic.
It is pretty fascinating. Pulsed electric fields, or PEF, is a really advanced pre-treatment technique.
Yeah.
Essentially, you're zapping the plant material with very rapid, very intense pulses of electricity.
Yapping it.
Yeah. This process, which is called electroporation, basically creates microscopic controlled nanopores. Think of them as tiny temporary holes in the plant's cell membrane.
Holes in the cells. What does that do?
What this does is significantly increase the diffusion coefficients. That's just a technical way of saying it allows molecules to migrate or flow much more easily and quickly from inside the plant cells out into an external solvent during extraction. It's like unlocking thousands of tiny gates that allow the desired compounds, if they're inside cells, to rush out more readily when the solvent arrives.
Nanopores you can control. That sounds truly innovative. Can they actually control what comes out through these pores? Can they be selective?
That's the truly innovative part and one of its major potential advantages. But precisely tuning the parameters of the electric field, the intensity, the pulse duration, the number of pulses, the size of those nanopores, can actually be controlled to allow for the selective release of molecules based roughly on their size, their atomic radius.
Like a sieve at the nanoscale.
Sort of. For instance, small water molecules can be rapidly driven out, effectively drying the plant material down to less than 10% water content by weight, without causing substantial loss of the much larger organic molecules like cannabinoids or valuable terpenes.
So the water gets out, but the good stuff stays in.
Exactly. Those larger molecules are retained within the plant material, held back by the size-selective pores until they actually come into contact with the extraction solvent later in the process. This means you can potentially dry the plant very efficiently using PEF without losing your valuable volatile compounds.
So it's not just efficient, but potentially smarter too, in terms of preserving the full profile of the plant.
That's the promise. The potential benefits are numerous. It's very fast, it can be highly energy efficient compared to thermal drying, and it's considered environmentally friendly as it doesn't use heat or chemicals for drying. It might even reduce the need for high pressure stages and some downstream extraction processes like supercritical fluid extraction, potentially saving on equipment wear and operational costs.
And it's gentle on the compounds.
Yes, because it's a non-thermal process, it minimizes the degradation of heat-sensitive compounds, like some of those aromatic terpenes we want to preserve. It helps maintain the overall flavor and therapeutic profile of the final extract. It's definitely a technology that's pushing the boundaries of pre-treatment efficiency and quality preservation.
Very cool. And finally, just to tie things back to our first section on decarboxylation, is decarbing the plant material itself considered a pre-treatment step before extraction?
Yes, absolutely. As we discussed earlier, decarboxylating the plant material before you start the extraction process is a very common and often preferred practice in the industry.
Especially with certain solvents.
Exactly, especially when the plan is to use nonpolar solvents like hexane or particularly supercritical CO2. This goes back to that solubility point. The neutral cannabinoids, THC, CBD, are just much more soluble in these nonpolar solvents than their acidic forms, THCA, CBDA. So, by doing the decarboxylation first, producers achieve significantly higher extraction yields and a more efficient overall process. It's really a synergistic step that primes the material for the best possible outcome with those types of solvents.
Okay, excellent. Now we're moving into the real heart of how these compounds are actually pulled from the plant after any pretreatment. Let's start with what are often called conventional extraction methods, moving from using liquid solvents to using pressurized gases. When we think about liquid solvent extraction, what's the basic principle at play here? How does it work?
The general principle is actually fairly straightforward. It relies on diffusion. The cannabinoids slowly spread out or diffuse from the plant's glandular trichomes, where they're concentrated, into the surrounding liquid solvent.
So basically a soaking process.
Essentially, yes. It's a soaking process where the target compounds dissolve into the liquid, separating them from the solid plant material. Often, the rate of diffusion, how quickly those cannabinoids move into the solvent, is the slowest part of the whole process. It's the rate-limiting step that determines the overall production output. So engineers are always looking for ways to speed up that diffusion.
And I imagine choosing the right liquid solvent isn't always easy. Is there one ideal solvent that does everything perfectly, dissolves only the good stuff, is safe, easy to remove, and cheap?
Ah, if only. Unfortunately, no, there's no single ideal solvent that ticks every single box. The choice always involves balancing several competing factors. You have to consider the solvent's selectivity, meaning how well does it dissolve just the cannabinoids versus pulling out other unwanted compounds like chlorophyll or fats and waxes. Then there's its toxicity. Is it safe for workers and residual levels in the final product? Its volatility, how easily can it be evaporated and removed from the extract later? And its flammability, which poses significant safety risks and requires specialized facilities. These considerations often force compromises that directly affect the scalability, the cost effectiveness, and the safety profile of the entire process.
Okay, let's talk about ethanol then. It seems to be a very common choice, maybe even something people try at home. What are its pros and cons from an industrial perspective?
Ethanol is indeed very popular, and for some good reasons. A big one is that it's generally recognized as safe, or GRAS, by regulatory bodies like the FDA. That's a huge plus, especially for products intended for human consumption.
Safety is key.
Absolutely. It also has high solvent power, meaning it's quite effective at dissolving both the cannabinoids we want and also the terpenoids, those compounds that give cannabis its characteristic aroma and flavor profile. Plus, it doesn't require extremely high pressures to work, which makes the equipment somewhat simpler and generally safer to operate compared to systems using, say, high-pressure hydrocarbons like butane. So it's relatively accessible and effective.
Sounds pretty good so far. What's the main drawback then? What makes ethanol less than ideal, forcing those compromises you mentioned?
The major drawback with ethanol, particularly when used at room temperature or warm, is its tendency to co-extract a lot of unwanted compounds along with the cannabinoids.
Like what kind of stuff?
This includes chlorophyll, which gives extracts that distinct green, sometimes grassy, and often unappealing tint. It also pulls out other pigments like carotenoids, some plant sugars called glycosides, and quite a bit of waxes and lipids from the plant material.
So it makes a dirty extract.
Essentially, yes. This dirty initial extraction means that more extensive and often costly post-processing steps are needed to purify the extract. You have to remove all that unwanted stuff to get a clean, high-quality final product suitable for things like vape pens or edibles. This adds extra time, labor, specialized filtration equipment, and solvent recovery steps to the overall process.
Right, adding cost and complexity.
Yeah.
Now, I've heard people talk about cold ethanol extraction as a way around this. Does chilling the ethanol way down actually help with these co-extraction issues? Does it result in a cleaner product?
Yes, it's a significant improvement, and it's often considered the optimal approach when using ethanol for extraction these days. By chilling the ethanol, typically to very low temperatures, the range mentioned is from 5 degrees C down to as low as 80 degrees C, with around METIG of 45 degrees C often cited as a sweet spot.
It's really cold.
It is, but doing this minimizes the co-extraction of chlorophyll and other compounds such as triglycerides and waxes.
How does the cold help?
It works because at these very low temperatures, many of those unwanted compounds, like waxes and fats, become much less soluble in the cold ethanol. They essentially precipitate out or just don't dissolve well in the first place, while the cannabinoids remain relatively soluble. This allows for a more selective extraction of the target compounds.
So you get mostly just the cannabinoids.
You get a much cleaner, crude extract, yes. It still requires some filtration, but significantly less exhaustive filtration and purification steps are needed later on compared to a room temperature extraction. Now, the overall yield of total extracted material might be slightly lower with cold ethanol, but the efficiency of the entire process, including the downstream purification, is often much higher because you've saved so much effort on cleanup. It's generally seen as a worthwhile trade-off for a cleaner, higher quality starting oil.
Can you walk us through a practical example? How might this cold ethanol process actually work in an industrial setting, from the soaking stage through to filtering out those impurities?
Sure. You might imagine a large, jacketed stainless steel vessel where, say, approximately 50 liters of deeply chilled ethanol, let's say at -45 degrees C, are used for every 5 kilograms of dried, ground cannabis material.
Okay.
The plant material might soak in the chilled ethanol for a relatively short contact time, maybe just 5 minutes if the temperature is kept really low, say below -40 degrees C. Or, alternatively, the chilled ethanol could be continuously pumped through a column packed with the plant material in a closed-loop system to ensure efficient contact and extraction.
And after the soaking or pumping?
After the extraction phase, the resulting ethanol cannabinoid mixture, the micella, would then be pumped through a multi-stage filtration system, all kept cold. This often involves passing it first through various adsorbent media, maybe specialized activated charcoal to grab pigments, then perhaps different types of clay like bentonite, and then maybe fine silica particles.
What do those filters do?
They're designed to selectively capture and remove any remaining undesirable compounds that might have still dissolved. Things like residual fats, lipids, waxes, and any lingering chlorophyll that made it through the cold extraction. Even with deeply chilled ethanol, some minor impurities might still be present. So these further filtration steps, all performed while keeping everything chilled, are crucial for achieving that high level of purity needed for many final products. It's a careful, multi-step dance to get a truly clean, high-potency oil.
Okay, so cold ethanol helps clean things up significantly. What about other types of liquid solvents, specifically non-polar ones like hexane or petroleum ether? How do they stack up, and are they still commonly used given the alternatives?
Non-polar solvents like hexane offer a different set of advantages and disadvantages, but generally their use is less common now, primarily due to safety and environmental concerns. Hexane, for instance, is actually quite good at dissolving cannabinoids, and a key advantage is that it doesn't co-extract much chlorophyll, which is great for the color of the final product.
Sounds good.
But hexane is toxic if inhaled or ingested, and it's highly flammable, posing significant safety risks that require expensive explosion-proof facilities and stringent handling protocols. It also tends to co-extract a good amount of waxes and lipid material from the plant, which then necessitates an additional, often energy-intensive, purification step called winterization to remove them by chilling and filtering. Plus, extraction times with hexane can vary widely in practice, reported anywhere from 1 hour up to 72 hours, which adds variability to production cycles.
And petroleum ether.
Petroleum ether is another nonpolar option. Its main appeal is low cost. However, it suffers from inconsistency between suppliers, often contains high levels of impurities itself, and shares the high flammability and toxicity concerns with hexane. While studies show it can achieve high CBD and THC extraction efficiencies, its industrial use is pretty limited nowadays due to these significant drawbacks and the associated safety liabilities. Ethanol and CO2 are generally preferred.
Right, the safety aspect is huge. Now, this next one is quite interesting because it seems to combine the extraction step directly with the final product formulation. Tell us about using vegetable oils like olive oil, coconut oil, or flaxseed oil for extraction. Is this a common industrial method or more for specific niches?
It's more for specific niches, but it's a very clever approach for certain applications. This method is primarily used for producing cannabinoid formulations that are directly intended for pharmaceutical or nutritional products like tinctures or capsules, where the final product is already diluted in a food-grade carrier oil.
So the oil used for extraction is the final product base.
Exactly. The big advantage here is that it completely avoids the need for a separate, often complex, energy-intensive, and potentially costly solvent removal step because there's no volatile solvent like ethanol or hexane to get rid of.
I see. Big simplification.
Huge simplification. It also bypasses the use of potentially toxic hydrocarbon solvents altogether, making it a much more environmentally friendly and potentially more cost-effective option compared to traditional methods that require extensive solvent recovery and purification. The resulting extract, being already in an oil base, can often be used directly for oral or topical applications, which is super convenient for producing certain types of consumer products.
That sounds incredibly convenient and safe. But there have to be some significant downsides, right? Otherwise, why wouldn't everyone do it this way? What limits its use?
Yes, there are definitely significant trade-offs that limit its industrial scalability, especially if you're aiming for high-potency products or purified cannabinoids. Firstly, this method typically requires comparatively higher extraction temperatures than, say, cold ethanol. The range is often between 30 and 80 degree DA, 86 to 176 F.
And that heat is a problem.
It can be. Those temperatures can potentially affect the integrity of some of the more heat-sensitive compounds in the plant, particularly the volatile terpenes that contribute aroma and flavor. So you might end up with a less full-spectrum product compared to colder methods.
Okay, what else?
Crucially, vegetable oil extraction results in much, much lower cannabinoid concentrations in the final extract compared to extractions done with volatile solvents that are later removed. The resulting product is inherently not pure cannabinoids. It contains all the vegetable oil used as the solvent. Its final cannabinoid concentration is limited by both the potency of the starting plant material and the amount of oil used for the extraction. You can't really concentrate it further to make high-dose products.
So it's always diluted.
Always diluted. It's great for making ready-to-use tinctures or topicals at standard consumer potencies, but not suitable if you need a concentrated oil for vape cartridges or high-potency edibles, or if you need to isolate pure CBD or THC.
Could you give us an example of how this kind of vegetable oil extraction might work, maybe in a more simplified setting? How do they get the cannabinoids into the oil?
One method described in the literature involves using mechanical extrusion. In this process, the cannabis plant material is essentially pressed and mixed intimately with a carrier oil, like flaxseed oil, often under moderate heat, maybe up to 80 degrees C, and relatively low pressure, perhaps around 10 bar.
Pressing and mixing with hot oil.
Right. This combination of pressure, heat, and mixing helps the cannabinoids diffuse from the plant trichomes into the surrounding carrier oil. This specific method was noted to produce an oil containing the acidic form, THCA, while also preserving many of the delicate terpenes, likely because the temperatures, while warm, weren't excessively high.
And what kind of concentration would you get?
Well, as an example, if you were to use, say, 10 kilograms of the carrier oil mixed with just 1 kilogram of cannabis flowers that initially contain 10% THCA by weight, the process might yield perhaps 3 liters of the extracted oil. The final product in this example might have a THCA concentration around 0.2% or maybe 30 milligrams per milliliter. This is actually a pretty standard concentration for some types of direct-use pharmaceutical or nutraceutical formulations. So it illustrates how the product is ready for direct application, but at a significantly lower cannabinoid concentration than extracts obtained via more aggressive solvent methods where the solvent is removed. It's truly a method designed for creating the final diluted, ready-to-consume product directly.
Okay, that makes sense. A very different approach for a different end goal. Now let's shift gears from liquids to gases used under pressure. What are the general advantages of using these pressurized gas extraction techniques? Why are they often preferred, especially for high-quality medicinal products?
The main advantages of pressurized gas extraction methods really center around product purity and the ease of solvent recovery. The solvents used are typically gases at room temperature and pressure, like butane, propane, or carbon dioxide, that become liquid under pressure.
Right.
Because they are gases naturally, they are incredibly easy to purge or remove from the final extract. You simply release the pressure and the gas evaporates away. This leads to almost complete solvent recovery and, more importantly, leaves behind very minimal, if any, solvent residues in the final cannabinoid product.
Good Brody.
Much cleaner. This is a critical advantage, especially for medicinal and pharmaceutical products where purity, safety, and meeting strict regulatory limits on residual solvents are absolutely paramount. You don't want leftover butane in medicine.
Definitely not. Okay, let's start with the gaseous hydrocarbons, things like butane and propane. What's the appeal of using these, but also what are the major risks that producers have to manage carefully?
The appeal is quite strong for certain types of products, particularly for making highly concentrated extracts like shatter, wax, or oils for vape pens. These solvents, butane and propane, often used individually or as a blend, are easily removed due to their very low boiling points, which, as we just said, leads to high purity in the final product. Often, over 90% cannabinoid content is achievable.
High potency.
Very high potency. And crucially, a huge advantage they have over ethanol is that they generally do not dissolve chlorophylls.
Ah, no green extracts.
Exactly. This eliminates a major post-processing headache associated with ethanol, the need to remove those green pigments. This makes hydrocarbons ideal for selectively extracting the neutral cannabinoids, assuming prior decarboxylation, and those desirable terpenes, resulting in a cleaner, more aesthetically appealing concentrate right off the bat.
Okay, sounds great for concentrates, but they come with pretty significant risks, don't they? We often hear stories, unfortunately, about explosions related to butane extraction, especially in amateur setups.
Absolutely. The major drawbacks are severe. These hydrocarbons are extremely flammable, and their vapors can form explosive mixtures with air. They can also be toxic if inhaled. This means that commercial facilities using butane or propane require significant, very expensive safety infrastructure. We're talking explosion-proof rooms, extensive ventilation systems, spark-proof equipment, continuous gas monitoring, and specialized training for personnel due to the inherent and serious risk of fire or explosion.
So high setup costs and strict protocols.
Very high. Furthermore, while they don't pull chlorophyll, they do tend to co-extract waxes and lipids from the plant, similar to Iceni. This again necessitates that additional winterization purification step to remove the waxes and achieve a clear, stable final product. And finally, scaling up these hydrocarbon extraction processes safely and efficiently can also be difficult. It often requires running multiple smaller batch units in parallel rather than large continuous systems, which adds to operational complexity and labor costs.
Right. Now, you mentioned these are the solvents often used to make those really popular cannabis concentrates like shatter and wax. That process sounds fascinating. How do they actually go from plant material to something like a brittle, glass-like slab of shatter or a soft, waxy substance?
Yes, that's precisely what hydrocarbons are often used for. It's a highly specialized process that requires careful control, especially of temperature. The starting material is usually cannabis plant material that has been frozen immediately after harvest, sometimes called fresh frozen, and kept frozen and dehydrated. This helps preserve the most volatile terpenes and prevents degradation.
Frozen material.
Okay. This frozen material is then packed into an extraction column, and the extractor itself is performed at very low temperatures, typically somewhere between -5 degrees C and -40 degrees C. 23F down to -40F.
What's so cold?
The purpose of these extremely cold temperatures is to essentially immobilize the unwanted lipids, fats, and any water-soluble molecules within the plant material. Freezing them makes them much less likely to dissolve into the cold hydrocarbon solvent, ensuring a cleaner extraction right from the start.
Makes sense. Then what?
Then, the cold liquid hydrocarbon solvent butane or propane, kept liquid under moderate pressure, is pumped through the packed column of frozen plant material. The cannabinoids and terpenes dissolve into the cold solvent. Once the extraction is complete, the solvent, now loaded with the desired compounds, is collected in a separate vessel. The next crucial step is removing that volatile hydrocarbon solvent.
How do they do that safely?
This is typically done by carefully applying heat, often using a jacketed collection vessel, while simultaneously pulling a vacuum. The combination of gentle heat and vacuum lowers the boiling point of the butane or propane, causing it to rapidly evaporate. The evaporated solvent gas is then usually recovered, condensed back into a liquid, and pumped into a holding tank for reuse, making it a closed-loop system for efficiency and safety. What's left behind is the concentrated cannabis oil.
Okay, so that gets you the oil. But how do they achieve those very different, distinct textures? The clear, brittle shatter versus the opaque, soft wax. Is it just a matter of how it cools down, or is there more to it?
It comes down to the specific post-extraction processing or purging techniques applied to that crude extract after the bulk of the solvent is removed. It's all about controlling the final stages of solvent removal and how the cannabinoid molecules settle or crystallize.
How do they make shatter?
To produce shatter, which is known for its clear, brittle, glass-like appearance, the concentrated oil, sometimes called a cookie or slab at this stage, is typically spread thinly and heated under a deep vacuum at relatively lower temperatures, maybe somewhere between 21 degrees C and 43 degrees C, 70 to 100 F, for an extended period, perhaps 15 minutes, maybe up to 48 hours, depending on the amount and desired clarity. Sometimes it's followed by a brief heating step at slightly higher temperatures, like 71-98 degrees C, 160 to 208 F, often under atmospheric pressure, until it becomes completely clear and transparent like glass. The slow, meticulous heating under vacuum allows any remaining solvent to purge out slowly without agitation, letting the cannabinoid molecules settle into a stable, uniform, amorphous, non-crystalline structure that becomes brittle when cool.
And for wax, how's that different?
For wax, which has a softer, more opaque, sometimes crumbly or buttery texture, the process involves more agitation. After the initial bulk solvent removal, the concentrated oil or cookie is heated to slightly higher temperatures than for shatter, maybe around 51-63 degrees, 125-145 F. Critically, during this final heating and purging phase, the extract is continuously stirred, whipped, or agitated.
Whooping the oil.
Essentially, yes. This constant agitation prevents the cannabinoid molecules from settling into that stable, glassy structure needed for shatter. It incorporates tiny air bubbles and disrupts any potential crystal formation, leading to an opaque appearance and a softer, waxier consistency. This agitation helps ensure the final product is typically free of residual solvent and chlorophyll, but results in a completely different physical form factor compared to shatter.
Fascinating how processing changes the texture so much. All right, let's move on to what's often considered the clean standard in the industry, especially for medicinal products. It's supercritical CO2, or CCO2 extraction. First off, what exactly is supercritical CO2? It sounds very sci-fi.
It does sound a bit sci-fi, but it's based on well-understood physics. Supercritical CO2 refers to carbon dioxide that has been heated and pressurized beyond its critical point. For CO2, that specific point is a temperature above 31 degrees C, about 88 degrees era, and a pressure above 73 bar, around 170 psi.
So, hot and high pressure, what happens then?
When CO2 is pushed beyond this critical point, it enters a unique supercritical state where it exhibits properties of both a liquid and a gas simultaneously. It has the density similar to a liquid, which makes it an excellent solvent, capable of dissolving other substances effectively. But at the same time, it has the low viscosity and high diffusivity, more like a gas.
Flows like a gas, dissolves like a liquid.
That's a great way to think about it. This gas-like property allows it to penetrate porous materials like ground cannabis very efficiently, getting into every nook and cranny. This unique combination of liquid-like dissolving power and gas-like penetration makes supercritical CO2 a powerful and very versatile solvent, especially favored for creating highly pure extracts.
Okay, I get the concept. What are the main advantages then? Why is it so widely adopted and often considered the gold standard, particularly for high-end or medicinal products?
The biggest advantages really revolve around safety, purity, and environmental friendliness, which is why it's so popular for medicinal applications. Firstly, CO2 itself is non-toxic and non-flammable, which dramatically reduces the safety risks compared to flammable hydrocarbon solvents.
Big plus there.
Huge plus. Secondly, and crucially, it can be easily and almost completely removed from the final extract simply by decreasing the pressure back below the critical point. When you reduce the pressure, the CO2 reverts to its normal gaseous state and simply evaporates away, leaving behind a virtually residue-free product.
So no leftover solvent taste or concerns.
Exactly. This ability to produce extracts with essentially zero residual solvent makes CCO2 the preferred technique for many medicinal and pharmaceutical applications, where the complete absence of potentially harmful residues is paramount for patient safety and for meeting strict regulatory requirements. It's truly a clean extraction method in that sense. It's also environmentally friendly, as the CO2 can be captured and reused.
It sounds almost ideal. Are there any significant downsides or challenges to using CCO2? Why doesn't everyone just use this method?
Well, despite its advantages, yes, there are definitely trade-offs and challenges. While CTO2 is excellent for dissolving non-polar compounds like THC and CBD, especially after decarboxylation, it's generally quite inefficient for extracting more polar compounds. Their solubility in pure CCO2 is often low, which can limit the ability to capture the full spectrum of compounds present in the plant without modifications to the process.
Okay, less good for polar stuff. What else?
A significant drawback, especially compared to cold ethanol or hydrocarbons, is its tendency to co-extract large amounts of waxy material and lipids from the plant, particularly at higher pressures used for cannabinoid extraction.
So you get a waxy extract.
Yes, the initial crude extract from CCO2 can be quite waxy or pasty. This then requires further, often extensive and time-consuming purification steps, commonly known as winterization, similar to what's needed for hexane extracts to remove these waxes and achieve a clean oil. This adds significant cost, time, and complexity to the overall process. The resulting crude extract can also be quite complex and somewhat diluted compared to hydrocarbon extracts, often needing more exhaustive purification processes downstream to isolate specific cannabinoids if high purity is the goal.
And the equipment.
Lastly, the equipment required to handle the high pressures and precise temperature control needed for supercritical CO2 extraction is quite sophisticated pressurized equipment. It's very expensive to purchase, install, and operate compared to simpler methods like ethanol extraction. This creates a high barrier to entry for smaller producers.
Right, high capital cost. Now, I've also heard people mention subcritical CO2 extraction. Is that just a variation of the same thing, maybe used for different applications or to overcome some of the CCO2 downsides?
It is indeed a variation. Subcritical CO2 extraction operates at temperatures and pressures below the supercritical point. For example, temperatures might be kept closer to room temperature, say below 31 degrees C, and pressures below that 73 bar threshold. Under these conditions, the CO2 is simply in its dense liquid form, not supercritical.
Liquid CO2 instead of supercritical, what's the advantage?
Operating in subcritical conditions can offer certain advantages, primarily related to preserving the most volatile compounds and reducing unwanted co-extraction. Because the temperatures and pressures are lower, subcritical CO2 extraction is generally gentler and can result in better preservation of delicate, volatile terpenes, those important aroma and flavor compounds. It also tends to co-extract significantly less of that waxy material compared to supercritical CO2, as the solubility of waxes decreases markedly at lower temperatures and pressures.
So a cleaner, more terpene-rich extract initially.
Potentially, yes. This often results in a cleaner crude extract right out of the extractor, potentially requiring fewer or less intensive purification steps down the line. However, the trade-off is that liquid CO2 is generally a weaker solvent than supercritical CO2, so subcritical extraction typically results in lower overall yields and requires significantly longer extraction times to achieve comparable results. It's less efficient overall.
Makes sense. And what about using co-solvents with supercritical CO2? I think you mentioned ethanol earlier. Does adding something else to the CO2 improve things, or does it just complicate that clean aspect?
It often does improve things, particularly for broadening the range of compounds that can be extracted efficiently. Frequently, a small amount of a polar co-solvent, most commonly ethanol, is added to the supercritical CO2 stream.
Why add ethanol?
Adding ethanol increases the overall polarity of the supercritical fluid mixture. This significantly boosts the solubility of more polar cannabinoids, like the acidic forms if extracting non-decarboxylated material or other polar compounds of interest. It can substantially improve the overall extraction rates and yields, and sometimes even allows producers to use a lower solvent-to-feed ratio, less CO2 needed per kilogram of plant material, to achieve high recovery rates.
Sounds beneficial for yield. Any downsides to adding ethanol?
Yes, there's always a trade-off. Adding a co-solvent like ethanol can sometimes lead to slightly lower recovery of specific target compounds like THC from the plant material itself, maybe due to complex phase behavior. More significantly, it often leads to an increased co-extraction of other polar compounds that you might not want, potentially reducing the relative concentration or purity of your target cannabinoids in the initial extract. This might necessitate more intensive downstream purification steps to achieve high purity, somewhat negating the initial clean benefit of using CO2 alone. And of course, you now have to remove the ethanol co-solvent as well as the CO2. So it's always a balance between enhancing yield and maintaining selectivity and purity.
Okay, we've covered the conventional workhorses, the liquids, and the pressurized gases. But the world of extraction is constantly innovating, always looking for ways to be faster, cleaner, more efficient, maybe use less energy or solvent. Let's look at some of these alternative methods that aim to push those boundaries. What's the general premise behind these newer techniques? How do they try to improve on the conventional ways?
These alternatives, often called intensified or assisted, extraction methods generally aim to physically disrupt the plant's cell walls or structures using various forms of energy. This could be microwave energy, ultrasonic sound waves, or even intense fluid dynamics. The core idea is to enhance the release of the target compounds from the plant matrix, making them more readily accessible to the solvent, or sometimes even liberating them more directly, potentially speeding up the process or reducing the need for harsh solvents or conditions.
Sounds promising, like physically forcing the compounds out. But thinking back to where cannabinoids are mostly located on the surface in those trichomes, is there a potential caveat or downside to aggressively disrupting the internal cell walls of the plant when you're primarily after the surface resin?
That is an extremely important caveat, yes, and it's a key consideration for producers evaluating these techniques specifically for cannabinoid extraction. Because, as you rightly point out, the majority of the valuable cannabinoids are concentrated in those glandular trichomes on the surface of the plant material. Aggressively disrupting the cell walls inside the leaves and stems isn't always a huge unqualified advantage for getting the cannabinoids themselves out. In fact, it carries a significant risk. By breaking open those internal plant cells, you can inadvertently release large amounts of unwanted intracellular compounds.
Like what?
Most notably, chlorophyll, which leads to that undesirable green color and grassy taste. You might also release other pigments, proteins, or complex carbohydrates that you then have to remove through additional, often costly and complex purification steps. So while these methods can be powerful for extracting compounds locked inside cells, for surface compounds like cannabinoids, their aggressive nature needs careful management to avoid making the extract dirtier, not cleaner.
Interesting trade-off. Okay, let's delve into one of these. Microwave-assisted extraction, or MAE. How does this technique actually work? Is it literally like putting your cannabis in a giant industrial microwave oven?
In a simplified sense, yes, the principle is similar, though the industrial equipment is far more sophisticated and controlled than a kitchen microwave. MAE uses microwave energy, typically at a frequency around 2.45 gigahertz, to directly and rapidly heat the solvent and, more importantly, the residual moisture inside the plant cells themselves.
Heating the water inside the cells.
Exactly. This internal heating causes a very swift increase in temperature, and consequently, pressure builds up rapidly inside the cells. This internal pressure literally causes the cell walls to swell and rupture. This cellular disruption makes it much easier for the compounds contained within or near those cells, including cannabinoids, to dissolve into the extraction solvent that's present. Think of it as creating a rapid internal pressure cooker effect within each cell. The heating is almost instant, tends to be more uniform throughout the bulk material, and is generally much more energy efficient than conventional external heating methods that rely on slow conduction.
Okay, rapid internal heating and cell rupture. What are the main advantages and disadvantages of MAE when considering it for industrial cannabis extraction?
On the plus side, MAE offers that instant, uniform, and highly efficient heating. This can potentially reduce the amount of solvent required and significantly shorten the overall extraction times compared to traditional heating methods, which translates to lower operating costs and higher throughput. Some MAE systems can even be designed to perform decarboxylation simultaneously with extraction, potentially optimizing both processes into a single, faster step.
Sounds efficient. What are the downsides?
Well, MAE requires quite expensive and sophisticated microwave generation and reactor equipment, which can also have a relatively short operational lifespan due to the intense energy involved. A significant challenge historically with MAE has been scaling it up effectively for large-scale industrial production. Microwaves only penetrate materials to a limited depth. This means that simple, large, stirred vessels become very inefficient, as the microwaves can't reach the center. To overcome this limitation, MAE often requires specialized continuous flow reactor designs where the material flows through a microwave field in a thin layer or tube, which adds another layer of engineering complexity and cost. And, as we discussed, the aggressive cell disruption can lead to co-extraction of unwanted intracellular compounds.
Right, the purity issue again. Okay, next up, let's talk about ultrasound-assisted extraction, or UAE. How does this technique use sound waves, something we can't even hear, to help get the good stuff out? Sounds perhaps less aggressive than microwaves.
UAE uses high-frequency sound waves, typically in the range of 20 to 100 kilohertz, which is above the range of human hearing. These powerful sound waves are introduced into the mixture of plant material and solvent. The key mechanism at play here is what's known as acoustic cavitation.
Cavitation, what's that?
As these intense sound waves pass through the liquid solvent, they create rapidly alternating cycles of high and low pressure. During the low-pressure cycles, tiny microscopic bubbles or cavities form in the liquid. During the subsequent high-pressure cycles, these tiny bubbles violently collapse or implode.
Imploding bubbles.
Yes, and this collapse generates incredibly localized effects. Transient hotspots with temperatures potentially reaching thousands of degrees Celsius, pressures reaching hundreds of atmospheres, and powerful shock waves and liquid jets radiating outwards from the collapse point.
Wow, intense micro effects.
Extremely intense but very localized. These effects act like microscopic hammers or agitators. The shock waves and jets effectively erode the surface of the plant material, break apart cell walls, and create intense micromixing right at the solid-liquid interface. This enhances the penetration of the solvent into the material and accelerates the diffusion of the target compounds out into the solvent. It's like using sound to create millions of tiny, powerful washing machines at the microscopic level.
That sounds less aggressive overall than blasting microwaves, maybe. Are there benefits in terms of temperature control and preserving those delicate compounds we keep mentioning?
Yes, that's often highlighted as a major advantage of UAE. Because the heating effect is more localized and the intense mixing created by the ultrasound helps distribute heat quickly, UAE can often be carried out at relatively mild bulk temperatures, typically ranging from 20 degrees C up to maybe 70 degrees C, 68 to 158 F, and ideally even below 30 degrees C, 86 F for preserving sensitive compounds.
Cooler process.
Much cooler overall than MAE or high-temp solvent extraction. This is due to the efficient mixing reducing thermal gradients. These milder operating conditions lead to shorter extraction times compared to simple soaking, and very importantly, they can help preserve those heat-sensitive cannabinoids, and especially the volatile terpenes, which might otherwise degrade or evaporate at higher temperatures used in other methods. It's generally considered a relatively simple, reliable, and inexpensive technique to implement, at least at laboratory or pilot scales, and often requires smaller volumes of solvent compared to conventional methods.
Okay, milder temps, preserved terps, sounds good. What are the cons for UAE? What are the hurdles for wider industrial adoption or potential pitfalls?
While it's quite effective and relatively simple at smaller scales, scaling up UAE efficiently and effectively for large industrial volumes remains a significant challenge, similar in some ways to MAE, though for different technical reasons related to transmitting that ultrasonic energy uniformly throughout a large vessel. It can be difficult to achieve consistent cavitation intensity in very large reactors.
Okay, scaling is tough. Anything else?
Yes, another point is that if too high ultrasound power is used in an attempt to speed things up further, it can still generate enough localized heat to potentially increase the bulk temperature and risk degrading those thermolabile compounds you're trying to preserve. So power levels need careful control. And one final, perhaps less obvious, cautionary note from the literature. If the ultrasonic probes or transducers immersed in the solvent are not made of highly inert materials like specialized ceramics or titanium alloys, there's a potential risk of tiny metal particles eroding off the probe surface due to the intense cavitation, which could contaminate the extract. That's obviously a big no-no for purity standards in food or pharma-grade products.
Good point. Material choice matters. Okay, finally, in this alternative section, let's talk about something called hydrodynamic cavitation. How does this differ from the ultrasound method we just discussed? Does it still use collapsing bubbles? And does it perhaps promise greater scalability?
Hydrodynamic cavitation is distinct from UAE, acoustic cavitation, because it doesn't rely on an external source like an ultrasonic transducer to create the cavitation bubbles. Instead, hydrodynamic cavitation occurs more naturally within a turbulent fluid flow itself when the conditions are right.
Generated by the fluid flow. How?
It's created by inducing a sudden change in the velocity and pressure of the moving fluid. Typically, this is done by forcing the liquid solvent, often containing suspended plant particles, to pass rapidly through a constriction in the pipe or flow channel. This could be a specially designed orifice plate, a plate with a hole in it, or a venturi tube, a tube that narrows and then widens again.
Like squeezing the flow.
Exactly. As the fluid speeds up dramatically to pass through that narrow constriction, its pressure drops sharply according to Bernoulli's principle. If the pressure drops below the vapor pressure of the liquid at that temperature, cavitation bubbles spontaneously form within the flow. Then, immediately downstream of the constriction, as the flow channel widens and the fluid velocity decreases, the pressure rapidly recovers. This pressure increase causes the newly formed cavitation bubbles to violently collapse, just like an ultrasound, generating those intense shock waves and microjets that disrupt the plant material suspended in the fluid.
Ah, so it's more about clever fluid dynamics and engineering the plumbing rather than needing external energy waves like ultrasound.
Precisely. The energy for cavitation comes directly from the kinetic energy of the flowing fluid itself, manipulated by the geometry of the flow path. And this difference is key for scalability. Because the cavitation is generated internally by the flow, hydrodynamic cavitation systems are generally considered to be more energy efficient and, critically, much easier to design and implement at a large industrial scale compared to ultrasonic cavitation, which is often limited by the effective range and power output of the external ultrasonic transducers. It's easier to build large pipes with constrictions than large, powerful ultrasound systems.
So potentially better for big operations. What are the claimed benefits?
Hydrodynamic cavitation systems promise many of the same benefits as UAE-enhanced cannabinoid release due to cell disruption, faster extraction times, potentially less solvent consumption, and possibly improved product quality due to efficient mixing and mass transfer, but with the added advantage of better scalability and potentially lower energy costs. It's considered a very promising, potentially low-cost extraction intensification technique with high recovery rates reported for various bioactive compounds, and it's still an active area of research and development specifically for cannabis extraction.
It sounds like it has a lot of potential pros. What are the current cons, or why isn't everyone using it already if it's so scalable and efficient?
The main drawback currently is probably that while promising, it still requires more sophisticated pumping systems and reactor designs compared to simple conventional soaping methods. And perhaps more importantly, detailed, peer-reviewed comparative yield and quality data directly linking its performance for cannabis extraction specifically against other well-established industrial techniques like large-scale cold ethanol or CCO2 setups are still less widely available in the public literature compared to the more mature methods. So its full impact on overall process efficiency, extract quality, and long-term cost-effectiveness in the specific context of high-volume cannabinoid production is still being fully explored and proven out by the industry. It's definitely on the cutting edge.
Gotcha. Still emerging but promising. Now, it's clear that the world of extraction is incredibly diverse, with all these different approaches, each with pros and cons. Do industrial processes often end up combining these different techniques?
Yeah.
Like using a pre-treatment method followed by a specific solvent, or maybe blending two methods together to get the best of all worlds?
Absolutely. That's very common in sophisticated industrial operations. Many processes are designed to combine different techniques in sequence or even simultaneously to truly optimize the overall efficiency, the purity of the final product, and to reduce the total processing time and costs.
Can you give an example?
Sure. This could involve using a physical pretreatment like milling or freeze drying, followed by maybe PEF, then going into a primary cold ethanol extraction. Or you might see stripping or pre-washing steps using one solvent to remove certain unwanted compounds before the main cannabinoid extraction with another solvent. Another common optimization is incorporating the decarboxylation step directly into a single heating stage that's part of the solvent recovery or final purification process, saving energy and time. These combined, optimized processes can involve high temperatures, precise pressure control, multiple solvents, and very sophisticated, often custom-designed equipment, which of course all gets factored into the final cost of the product on the shelf. The goal is always to find the most efficient, safe, and cost-effective pathway to produce the specific final product they're aiming for at the scale they need.
Right. It's all about optimization. So when we try to connect all of this incredibly detailed information back to the listener, what's the big takeaway message here? How does a producer ultimately choose which path to take? From something as simple as, decarbing in a home oven and making infused butter, all the way up to these incredibly high-tech, multi-million-dollar PEF or CCO2 systems.
The choice of method ranging from that simple baking in your kitchen oven, maybe using vegetable oil infusion, right up to advanced pulsed electric fields pre-treatment followed by complex, multi-stage, supercritical CO2 extraction with co-solvents, it really depends entirely on the desired final product. That's the primary driver.
What are they trying to make?
Exactly. Are they aiming to produce a relatively simple, full-spectrum oil with all the natural terpenes intact for a tincture? Or are they trying to manufacture a highly purified, crystalline isolate of CBD or THC that needs to meet strict pharmaceutical standards? Or perhaps they want to create a specific cannabinoid and terpene profile tailored for a targeted therapeutic effect or a particular consumer experience in a vape pen. Each of these end goals might favor a very different extraction and purification strategy.
Makes sense. And beyond the product itself.
Beyond the product specs, the other absolutely critical factors are the available budget, both for the initial capital investment in equipment and for the ongoing operational costs, the stringent safety considerations for their workers and the facility, especially with flammable solvents or high pressures, and, of course, the desired scale of production. A small batch artisanal producer focusing on craft quality might choose a very different, perhaps more labor-intensive path than a large multinational pharmaceutical company manufacturing GMP-grade ingredients, or a massive recreational cannabis cultivator processing tons of biomass per day. Each method is really just a tool in the toolbox, and selecting the right tool or combination of tools depends entirely on the specific job they need to do.
What's truly fascinating to me after hearing all this is just the sheer unseen complexity that lies behind what might seem like relatively simple cannabis products sitting on a store shelf or prescribed by a doctor. It's really a whole hidden world of precision science and engineering.
I agree completely. Behind that unassuming bottle of CBD oil, or that package of gummies, or even a highly refined concentrated vape cartridge, there exists this fascinating, intricate world of precise chemistry, clever chemical engineering, sophisticated analytical testing, and continuous, ongoing innovation. Scientists and engineers in this field are constantly working, experimenting, and refining these processes to optimize purity, maximize the yield of valuable compounds from the plant material, ensure safety and consistency, and ultimately enhance the consumer experience, whether that's for recreational enjoyment, general wellness, or critical therapeutic purposes for patients. It's really a powerful testament to how applied science and engineering are used to transform natural plant resources into highly specific, refined, and functional products, constantly pushing the boundaries of what's possible with plant-based compounds.
Wow, we have really covered a lot of ground today, haven't we? We've gone from the fundamental chemistry of decarboxylation, really understanding why that little A on THCA and CBDA matters so much, and digging into how heat can both activate and unfortunately destroy these compounds, if not controlled perfectly.
That critical balance.
Exactly. And then we explored this whole diverse world of cannabinoid extraction techniques. We've looked at everything from classic liquid solvent washes using ethanol warm, or even better, very cold or older methods with things like hexane, all the way up to using high-pressure gases like butane for concentrates, or the clean standard of supercritical CO2.
Yeah.
And we even touched on those cutting-edge methods using microwaves, ultrasound, and even pulsed electric fields.
It's a huge range of technologies.
It truly is. It's become incredibly clear that getting the most out of the cannabis plant and getting exactly what you want out of it is this really complex dance involving precise control of temperature, time, pressure, solvent choice, and some very clever engineering, all aimed at delivering specific, consistent, high-quality products to consumers and patients.
And, this constant drive for innovation in cannabinoid science and these increasingly sophisticated extraction and purification methods, it naturally raises a really important and exciting question for the future. What new medical applications, what novel consumer products, or perhaps even entirely new fundamental understandings of plant chemistry might these increasingly precise and efficient techniques unlock next? The potential for further discovery and for developing new uses for these compounds, both the ones we know well and perhaps minor ones we haven't fully explored yet, it feels truly vast.
That is a great thought to end on. What else is waiting to be unlocked? Now, if you, our listeners, found this deep dive into the science behind cannabis processing as fascinating as we did, and if you learned something new today about how these products are actually made, then please do remember to hit that like button or leave a positive rating wherever you're listening.
It really helps others find the show.
It does. And please share this deep dive with someone else you know who loves learning about the hidden complexities behind everyday things. And of course, make sure you subscribe to the deep dive so you don't miss our future explorations into the incredible stories hidden in the science all around us. Your support truly helps us keep uncovering these fascinating topics and bringing you more in-depth knowledge. Thanks so much for listening.